Scratch the back of your hand. Go ahead. Use your fingernail. Drag it across your skin. You feel that? A little white line. Maybe it stings for half a second. On Earth, that scratch is nothing. It heals before you remember it happened. Now I want you to imagine the same scratch, same fingernail, same depth, same tiny, trivial, laughable little mark on your skin, except this time it happens on the outer layer of a spacesuit, outside, in orbit, 200 miles above where you're sitting right now. That scratch kills you. Not eventually, not probably. It kills you in about 90 seconds. And I want to explain exactly why, because the physics behind that fact is some of the most beautiful and terrifying physics I know. It all comes down to something you have never once in your life thought about, even though it has been pressing on every square inch of your body since the moment you were born. Let me start with something absurdly simple. I want to talk about a pot of water on your stove. On your stove. You put the pot on the burner. You turn up the heat, and at some point the water starts to boil. Everyone knows this. The water boils at 212 degrees Fahrenheit, 100 degrees Celsius if you prefer. Fine, but here is the question nobody asks. Why that temperature? What is special about 212 degrees? The answer has everything to do with a fight, a contest, a tug of war. See, inside that pot, the water molecules are bouncing around, jiggling, vibrating, doing what molecules always do when they have thermal energy. Some of them are moving fast, some slow, but on average they are bumping into each other and bumping into the surface of the water. The faster ones, the energetic ones near the surface, they want to escape. They want to fly off into the air as vapor. They are trying to leave, but something is pushing back. Something is sitting on top of that water, pressing down. The atmosphere, the air in the room, all that air above you, miles and miles of it, stacked up from the ground all the way to the edge of space. That column of air is heavy. It weighs about 14.7 pounds on every square inch of surface. We call that one atmosphere of pressure. And that weight, that pressure, is pushing down on the surface of your water, telling those molecules, no, you stay put, you are not going anywhere. So the boiling point of water is not some fixed law of the universe. It is the temperature at which the water molecules finally have enough energy to win the fight against the air pressing down on them. That is all boiling is. It is the moment the molecules say, I am stronger than the atmosphere, and they escape. Now here is where it gets interesting. What if I change the rules of the fight? What if I take away some of the atmosphere? You have probably noticed, if you have ever been to a high mountain, that water boils at a lower temperature up there. In Denver, Colorado, about a mile above sea level, water boils at roughly 202 degrees instead of 212. There is less air above you, less weight pressing down, so the water molecules do not have to fight as hard. They escape sooner. At the top of Mount Everest, nearly 30,000 feet up, water boils at about 158 degrees. You could make tea up there, but it would be lousy tea because the water is not hot enough to extract the flavor properly. All right, so the pattern is clear. Less pressure, lower boiling point. Less pressure, lower boiling point. You keep going up, the pressure keeps dropping, the boiling point keeps falling. At the top of Kilimanjaro, water boils at about 160 degrees Fahrenheit. In a vacuum jar in the laboratory, you can make water boil at room temperature. I have done this. I put a flask of water on the bench, connected it to a vacuum pump, and watched the water start to bubble and churn without any heat at all. It looks wrong. It looks like a magic trick. You stare at this flask of room temperature water that is actively boiling, and your brain does not want to accept it. That cannot be right, your brain says. Water boils when it is hot. No. Water boils when the vapor pressure of the liquid exceeds the ambient pressure above it. Temperature is just one way to change that balance. Lowering the pressure is the other way. And by the way, this is not esoteric physics. This is the same principle behind freeze-drying food. You put the food in a vacuum chamber, lower the pressure, and the water in the food evaporates right out of it at low temperature. This is also why your tongue dries out faster at high altitude, even though you are not dehydrated. The moisture is evaporating more readily because there is less air pressing down to keep it liquid. Your body is already losing the fight, and you do not even realize it. Now I want you to follow this idea all the way to its logical, horrifying conclusion. How far can we go? There is a boundary, a specific altitude, a line in the sky. Above this line, the atmospheric pressure drops so low that the boiling point of water falls to 98.6 degrees Fahrenheit, 37 degrees Celsius. Do you recognize that number? That is the temperature inside your body. Right now, the temperature of your blood, your saliva, the fluid coating the inside of your lungs. This boundary sits at roughly 63,000 feet, about 12 miles up. It is called the Armstrong limit, named after a United States Air Force physician named Harry George Armstrong, who first realized what this altitude meant. And what it means is this: above the Armstrong limit, exposed body fluids begin to boil, not because they are hot, because the pressure is too low to hold them together as liquid. Let me say that again, because people hear the word boil and they think of heat. They think of a kettle screaming on the stove. This is not that. Your body is not getting hotter. The air around you is getting thinner. The atmosphere is letting go, and without that external squeeze, the water inside you begins to convert to vapor at your own normal body temperature. The saliva on your tongue bubbles. The moisture in your eyes starts to fizz. The thin film of liquid lining the tiny air sacs in your lungs turns to gas. A man named Jim LeBlanc experienced this firsthand. And in 1966, he was an aerospace engineer at NASA's Johnson Space Center in Houston, and he was testing a prototype spacesuit inside a giant vacuum chamber. This chamber was enormous, big enough to hold a spacecraft, and they pumped all the air out to simulate the conditions of space. LeBlanc was inside wearing the suit, and everything was going fine until the pressurized air hose feeding into his suit disconnected. Just like that, a hose came loose. The pressure inside his suit plummeted. In a matter of seconds, it went from a survivable, breathable atmosphere to almost nothing. And the last thing LeBlanc remembered before he lost consciousness was the feeling of the saliva on his tongue beginning to bubble, to boil, at normal body temperature. Not because anyone heated his mouth, because the air left. The technicians outside the chamber saw what happened and scrambled to repressurize. They got the pressure back up in about 30 seconds. LeBlanc woke up, he was fine, he went back to work. But think about what happened in those few seconds. His own body became the experiment. He felt the physics of phase transition on his own tongue. The boundary between liquid and gas moved right through him, and the only thing that saved his life was the speed of the people watching. 14 seconds. That is about how long he had before he blacked out. If repressurization had taken 2 minutes instead of 30 seconds, we would not know his name. He would be a fatality report in a filing cabinet. Now, space is worse, much worse. Space is not 63,000 feet. Space is not thin atmosphere. Space is nothing, zero, or so close to zero that the difference does not matter. In low Earth orbit, the pressure outside a spacecraft is roughly 1/trillionth of what you feel right now sitting wherever you are. 1/trillionth. You might as well call it nothing. And it is not just the absence of pressure. It is the absence of everything. It's no air molecules to breathe, no air molecules to conduct heat, no air molecules to carry sound, no ozone layer to block ultraviolet radiation, no magnetosphere to deflect the worst of the solar wind, although at low orbit you still get some protection from Earth's magnetic field. It is the most complete emptiness you can find in the natural world, and it is right there 200 miles above your head. That is less than the distance from New York to Washington. You could drive it in a few hours. But those 200 miles straight up take you from the most comfortable environment on Earth to the most lethal environment humans have ever entered. So now I want you to think about what stands between an astronaut and that nothing, a spacesuit. 13 layers of fabric. That is it. 13 layers of material, each one doing a specific job, sewn and bonded together into a garment that weighs about 110 pounds on the ground. And it is the only thing between a human being and instant violent death. Let me walk you through what those layers actually do, because most people imagine a spacesuit as some kind of thick armored shell. It is not. It is more like a sandwich. A very carefully designed sandwich where each ingredient has a purpose, and if you remove any single ingredient, the sandwich kills you. The innermost layer is a cooling garment. It is basically long underwear laced with tiny plastic tubes, and cold water runs through those tubes to pull heat away from the astronaut's body. See, in a vacuum, there is no air to carry heat away from you. No convection. The only way to lose heat is through radiation, which is extremely slow when you are wrapped in an insulated suit. Without active cooling, an astronaut would cook inside their own suit within hours. The sweat would fog up the helmet, the body temperature would climb, So the first job of the suit is to keep you from overheating. Above that cooling garment, you get the pressure layer. This is the bladder. It is made of a urethane-coated nylon, and it is airtight. It holds in the oxygen. The suit is pressurized with pure oxygen at about 4.3 pounds per square inch. That is much less than the 14.7 pounds per square inch you feel right now at sea level, but it is enough. It is enough to keep your fluids liquid. It is enough to keep your lungs working. It is enough to win the fight against the vacuum outside. Surrounding the bladder is a restraint layer made of Dacron, which gives the suit its structure. Without the restraint layer, the pressurized bladder would balloon outward like an inflated rubber glove, and the astronaut would be unable to move. The restraint layer contains the pressure and allows the joints to bend. And then on the outside you have the thermal micrometeoroid garment. This is where it gets serious. This outer shell has about 7 or 8 layers of aluminized mylar, separated by thin spacer fabrics, and the outermost surface is a tough woven material called orthofabric, which is a blend of Gore-Tex, Kevlar, and Nomex. The mylar layers work like the shiny emergency blankets you see in marathon finish lines. They reflect thermal radiation. In direct sunlight in orbit, the external temperature can reach about 250 degrees Fahrenheit. In shadow, it plunges to minus 250 degrees or lower. Those swings happen every 90 minutes as the station orbits the Earth, passing from day to night over and over. The mylar keeps that thermal chaos from reaching the astronaut. But the orthofabric and Kevlar layers have another job. They stop bullets. Not regular bullets. Something worse. Micrometeoroids. Tiny particles of rock and metal, fragments of comets and asteroids, grains of dust that have been orbiting the sun for millions of years. These particles are small. Some of them are smaller than a grain of sand, but they are traveling at speeds of 8 to 16 kilometers per second. Let me translate that for you. 16 kilometers per second is roughly 36,000 miles per hour. A bullet from a rifle moves at maybe 2,000 miles per hour. These specks of dust are going 18 times faster than a bullet. When something that small hits something else at that speed, it does not just poke a hole. It vaporizes on contact. It turns into a tiny jet of superheated gas that burns through whatever it strikes. The physics here is extraordinary, actually. At those velocities, the kinetic energy is so enormous that it exceeds the binding energy of the atoms in both the particle and the target. Everything in the impact zone turns to plasma. Solid metal becomes a gas in a millionth of a second. The impact creates a tiny crater, and a shock wave propagates outward through the material. The outer layer of the suit is designed to break up that particle, absorb its energy, and convert it from a solid projectile into a harmless cloud of gas before it reaches the pressure bladder underneath. The Kevlar fibers catch the fragments. The multiple mylar layers dissipate the shock. Layer after layer sacrifices itself to slow the destruction, like a series of nets catching a cannonball. Each layer absorbs a little more energy, spreads the impact over a wider area, and by the time whatever remains of the particle reaches the pressure bladder, it has lost most of its punch. And it works, most of the time. But there is also orbital debris, and this is a problem that gets worse every year. Thousands of pieces of junk from old satellites, spent rocket stages, fragments from collisions between defunct spacecraft, flecks of paint that have chipped off during thermal cycling. In orbit, even trash is lethal. In 1983, a tiny fleck of paint hit the windshield of the Space Shuttle Challenger and left a pit deep enough that the entire window had to be replaced after the mission. A fleck of paint, something you might brush off your jacket without thinking. But traveling at orbital velocity, it hit that window like a bullet. This is the environment in which a person goes outside for a spacewalk. Now here is what I want you to hold in your mind. The pressure bladder. The layer that keeps the oxygen in, that keeps an astronaut alive, is a sheet of coated nylon. It is thin. If something punches through the outer protective layers and pierces that bladder, the oxygen starts leaking into space. And in space, there is nowhere for it to go except out. The suit deflates. Not like a balloon popping, more like a slow, steady exhale that you cannot stop. The pressure drops. And as the pressure drops, the astronaut's body begins the same process Jim LeBlanc experienced in that vacuum chamber in 1966. Except there is no technician standing by to repressurize the room. The blood does not boil right away. This is a common misconception, and I want to clear it up because the real story is more interesting than the myth. Your blood is inside your circulatory system, which is a closed, pressurized system. Your heart is still beating. Your blood vessels and tissues are elastic. They hold in enough pressure to keep the blood liquid, even in a vacuum, at least for a short time. Even a person with low blood pressure has enough internal pressure to prevent the blood from boiling outright. The blood vessels are sealed. The heart is a pump. The system holds. What boils is the exposed fluid, the saliva on your tongue, the tears on the surface of your eyes, the thin film of liquid that coats the alveoli, the tiny air sacs deep in your lungs where gas exchange happens. These exposed fluids, the ones that are in direct contact with the ambient environment, they turn to vapor almost immediately. The evaporation of these surface fluids is what causes the initial cooling. Your tongue gets cold, your eyes sting. The inside of your lungs feels like they are burning, except it is not heat, it is the rapid evaporation of moisture pulling energy out of the tissue. Meanwhile, gases dissolved in your body begin to come out of solution. You know how a bottle of soda fizzes when you open the cap? That is carbon dioxide coming out of solution because the pressure dropped. The same thing happens in your blood and tissues, except with nitrogen. Tiny bubbles form in your joints and your muscles and your soft tissue. This is the same mechanism that causes decompression sickness in deep-sea divers who surface too quickly. They call it the bends because the bubbles in the joints are so painful that victims double over. In a vacuum, this process is much more severe. The bubbles do not just form in the joints. They form everywhere. The body swells, not like a balloon about to pop. The skin is too strong for that. But the tissue puffs up to roughly twice its normal volume. You would look like a caricature of a bodybuilder. Swollen everywhere, your skin stretched tight, and then the clock starts. You have roughly 15 seconds of useful consciousness. 15 seconds during which your brain is still working, still receiving enough residual oxygen from the last few breaths you took to function. After 15 seconds, the lights go out. Unconsciousness. Your body is still alive, technically, but you are gone. The heart keeps beating for maybe another minute or two, pumping blood that carries less and less oxygen. And somewhere around the 90-second mark, if the pressure is not restored, the damage becomes irreversible. The oxygen deprivation destroys brain cells. Your organs begin to shut down. The gas bubbles in your tissues expand further and cause massive internal disruption. The medical term for this process is ebullism. It is, in a very literal sense, the boiling away of a human being from the inside out. 90 seconds. That is the margin between we can bring you back and you are gone. And I have not even talked about temperature yet. Or the worst mistake you could make, which is holding your breath. If you ever find yourself exposed to vacuum, the single most deadly thing you can do is hold your breath. I know that sounds counterintuitive. Every instinct says the air is leaving, hold on to what you have. But the air in your lungs is at several pounds per square inch of pressure. The vacuum outside is at 0. If you seal your mouth and try to hold that air in, the pressure differential will rupture your lungs. The air expands violently and tears through the lung tissue like a paper bag bursting. Scuba divers know this rule. If you ascend quickly, you exhale continuously. You let the expanding air out. The same rule applies in vacuum. Exhale, let the gas go. It will save your life, because you will lose consciousness before your lungs can sustain lethal damage. And if someone repressurizes the area within 90 seconds, you have a chance. With ruptured lungs, you have no chance at all. In sunlight, the exposed side of the suit bakes. In shadow, it freezes. But the truth is, the temperature is almost irrelevant. You would die from pressure loss long before you had any meaningful thermal damage. The vacuum kills you so fast that the cold never gets a chance. In space, the vacuum is the executioner. The temperature is just standing in line behind it. So now let me come back to our scratch, that tiny scratch on the outer layer of the suit. What does it actually do? Well, it depends. If it only damages the outermost orthofabric, the astronaut is probably fine. That outer layer is tough, and a scratch that does not penetrate through to the mylar insulation underneath is a cosmetic problem, not a lethal one. But if it goes deeper, if it tears through the thermal layers, if it reaches the pressure bladder, then you have a leak. And a leak in space is a race against time. There was a real incident on shuttle mission STS-37 in April of 1991. Astronaut Jay Apt was outside performing a spacewalk. During the extravehicular activity, a stainless steel palm restraint bar punctured the pressure bladder of his right glove. A tiny hole. He did not even notice it. He continued his spacewalk, came back inside, and only discovered the puncture afterward. What saved him was remarkably low tech. His hand and the silk comfort glove underneath had partially plugged the hole. His own skin and a bit of cloth had blocked the leak. The depressurization was so slight it did not even register on the suit's instruments. But imagine that hole had been a little bigger. Imagine it had been in the torso, not the glove, where there was no hand to block it. Imagine it had been caused by a micrometeoroid strike instead of a piece of equipment. The difference between a story with a happy ending and a story with a dead astronaut is a matter of millimeters, a matter of how much fabric remains intact between the vacuum and the breathing gas. After that incident, and after similar glove damage on later missions, NASA changed its procedures. Now, during every spacewalk, astronauts are required to stop periodically and inspect their gloves. They look for cuts, abrasions, missing threads, anything that might indicate the outer layers have been compromised. Handrails on the outside of the space station that have been pitted by micrometeoroid strikes are flagged as hazards because a sharp edge left by a tiny impact could slice through the glove during a routine hand-over-hand traverse. The astronauts are given a list of specific handrails to avoid. Think about that. There are handrails in space that are too dangerous to grab. And the gloves, by the way, are the weakest point. They have to be everywhere else on the suit. The engineers can pile on thick layers of protection. The torso is actually a hard fiberglass shell. The helmet is polycarbonate. But the gloves need to be flexible. The astronaut has to be able to grip tools, turn bolts, manipulate small connectors. You cannot do that wearing a rigid gauntlet. So the gloves are thinner, more vulnerable, and they are the part of the suit that touches the most surfaces, encounters the most abrasion, takes the most abuse. The weakest point is also the most exposed. This is a pattern I have noticed in engineering, and I want to dwell on it for a moment because it matters far beyond spacesuits. The most critical failures tend to happen at the interfaces, the joints, the seams, the places where two systems meet, not in the thick overbuilt center of anything, but at the edges where flexibility is required and protection is hardest to provide. I saw this pattern up close when I was investigating the Challenger disaster in 1986. The space shuttle did not fail in its heat tiles, which everyone worried about. It did not fail in its main engines, which were enormously complex machines with turbopumps spinning at 30,000 revolutions per minute, running on liquid hydrogen and liquid oxygen at pressures that would make a plumber weep. It failed at a joint, a seam between two cylindrical sections of the solid rocket booster sealed by rubber O-rings. The O-rings were supposed to be flexible. They were supposed to expand and fill the gap when the rocket ignited, and the metal segments shifted under tremendous pressure. But on that cold January morning, the temperature at the launch pad had dropped to 32 degrees Fahrenheit. Ice was forming on the structure, and the rubber had lost its resilience. It had gotten stiff, brittle. It could not spring back fast enough to seal the gap when the booster segments flexed at ignition, and a jet of hot gas, 5,000 degrees Fahrenheit, burned through the O-ring, burned through the joint, reached the external fuel tank, and 73 seconds after launch, the shuttle broke apart. 7 people died. A rubber ring, about 1/4 of an inch thick. That was the margin. I demonstrated this failure at a hearing. I took a piece of the O-ring rubber, squeezed it with a small clamp, and dropped it into a glass of ice water. When I pulled it out and released the clamp, the rubber stayed flat. It did not bounce back. It had lost its resilience in the cold, just as it had on the launch pad that morning. The whole demonstration took about 30 seconds. The physics was that simple. And yet NASA had known about the O-ring problem for years, and had continued to fly. When I was on that investigation commission, I asked NASA management what they thought the odds were of a catastrophic failure. They said about 1 in 100,000. 1 in 100,000. That meant, according to them, you could launch a shuttle every day for 300 years and expect to lose only one. I thought that was insane. The engineers, the people who actually built and tested the hardware, put the odds closer to 1 in 100, maybe 1 in 200. The management was off by a factor of 1,000. And I realized something. The people in charge had gotten used to success. They had been flying shuttles for years, and nothing had gone catastrophically wrong, and so they started to believe that the absence of failure was proof of safety. I wrote in my report that this was like playing Russian roulette. The fact that the first shot did not kill you is not evidence that the gun is safe. It is evidence that you were lucky. This same logic applies to spacesuits. Every time an astronaut goes outside and comes back alive, there is a temptation to say the suits are safe, and they are remarkable pieces of engineering. Truly. I do not want to diminish the extraordinary work that has gone into designing them. But the margins are thin. The margins are always thin. Let me give you another number that will put this in perspective. The space station orbits at about 17,500 miles per hour. At that speed, it covers the length of a football field in about 100th of a second. A micrometeoroid the size of a grain of sand traveling in the opposite direction at orbital speed would have a closing velocity of maybe 40,000 miles per hour. The kinetic energy of that grain of sand at that speed is roughly equivalent to a bowling ball thrown at 60 miles per hour. Except all that energy is concentrated on an area smaller than the period at the end of a sentence. The outer layers of the suit are designed to handle particles up to a certain size. Beyond that, the engineers accept the risk. They calculate the probability of being hit by something too big for the suit to stop, and they make sure the probability is acceptably low for the duration of a typical spacewalk. Acceptably low. Not zero. Never zero. You cannot make it zero. There will always be a particle you did not account for, a piece of debris that was not tracked, a closing velocity that exceeds your design parameters. The astronaut goes outside knowing this. The engineers know this. Everybody involved in the decision accepts a level of risk that most people on the ground would find astonishing. But let me push this even further, because there is something else about space that most people do not consider. The vacuum itself is not just the absence of air. It is the absence of everything that air does for you that you never think about. Air distributes sound. In space, you cannot hear anything outside your suit. If your suit were tearing open behind your back, you would hear nothing. No ripping sound, no whistle of escaping gas. You might feel a change in pressure, maybe. You might notice the suit getting stiffer or softer. But by the time you notice, the clock is already ticking. Air transfers heat. Without it, the only thermal transfer is radiation, which is slow compared to conduction and convection. This means that when an astronaut moves from sunlight to shadow, the temperature change on the suit surface is extreme, but the suit insulation keeps it from reaching the body. However, if a section of insulation is damaged, if the thermal layers are compromised by that scratch we keep talking about, a patch of the pressure bladder could be exposed to direct sunlight. And direct sunlight in space, unfiltered by any atmosphere, includes the full spectrum of ultraviolet radiation. On Earth, the atmosphere blocks the most dangerous wavelengths. In orbit, there is nothing between you and the sun. A bare patch of nylon bladder exposed to direct solar radiation would degrade rapidly. The UV would break down the polymer chains. The material would become brittle. And a brittle pressure bladder, under 4.3 pounds per square inch of internal pressure, is a bladder that is about to rupture. So a scratch that only damages the outer layers might not kill you today, but it could weaken the suit in a way that kills you tomorrow, on the next spacewalk when the degraded material finally gives out. Air also blocks radiation. Not just ultraviolet, cosmic rays, high-energy particles from exploded stars and from the sun itself. On the ground, the atmosphere provides shielding equivalent to about 10 feet of water overhead. The spacesuit provides almost none. The suit is a pressure vessel and a thermal blanket. It is not a radiation shield. For the duration of a typical 6 to 8 hour spacewalk, the radiation exposure is manageable, but it is not zero. An astronaut on a spacewalk absorbs more radiation in a few hours than most people on the ground absorb in a year. I keep coming back to this word thin. Everything about human survival in space is thin. The margin of pressure, the layers of the suit, the window of consciousness, the line between a scratch that does not matter and a scratch that is fatal. And you know what? This teaches us something profound about where we live right now, because the same physics applies here. You are sitting right now at the bottom of an ocean of air. It is roughly 60 miles deep, give or take, depending on how you define the edge. And that ocean of air is doing everything for you. It is keeping your fluids liquid. It is filtering the radiation from the sun. It is distributing heat, so you do not freeze in the shade and cook in the sunlight. It is carrying sound to your ears. It is providing the oxygen your blood absorbs with every breath. Take it away, and you are dead in 90 seconds. Just like the astronaut with the torn suit. The difference is that on Earth, nobody is going to take it away. That the atmosphere is not going anywhere. It has been here for billions of years. But in space, the only thing between you and the total absence of everything your body needs is a garment. A garment designed by engineers, sewn by technicians, checked by inspectors, and worn by a person who has to trust that every stitch, every seal, every layer is exactly where it should be. This is what I meant when I told the Rogers Commission that for a successful technology, reality must take precedence over public relations, for nature cannot be fooled. You cannot talk your way out of a vacuum. You cannot hold a press conference to explain to the laws of physics that the suit was tested and certified. If the pressure bladder has a hole, the gas escapes. Period. Physics does not care about your confidence. It does not care about your schedule or your budget. It responds only to the actual state of the materials, the actual forces, the actual conditions. I think people have a hard time understanding how thin the margins are in space because they have never experienced a total absence of atmosphere. Every experience you have ever had, from the day you were born, has occurred inside this ocean of air. You have never felt what it is like for the pressure to drop to nothing. You have never experienced your own body fluids trying to become vapor. It is so far outside normal experience that the brain cannot really grasp it. It is like trying to explain color to someone who has never seen light. And so when I say that a scratch on a spacesuit could kill an astronaut, people nod politely, the way you nod when someone tells you a statistic about car accidents. Yes, very dangerous, how unfortunate. But they do not feel it. They do not feel the physics of it. So let me try once more. Put your hand flat on the table in front of you. Feel the air above your hand. You cannot feel it, of course. It is invisible and seemingly weightless. But there is a column of air stretching from your hand all the way to the top of the atmosphere, and it weighs about 14.7 pounds per square inch. Over your entire hand, that is roughly 100 pounds of air pressing down. You do not notice it, because the same pressure exists inside your body pushing outward. The forces balance. You live in equilibrium. Now imagine someone lifts that column of air off your hand. Just removes it, not gradually, all at once. What would happen? Your hand would swell. The moisture in your skin would begin to evaporate. Tiny blood vessels near the surface would distend. You would feel a pulling sensation, as if the vacuum were trying to suck everything out through your pores. It would not be pleasant, but your skin is strong. Your body is tougher than you think. If someone put the air back in 15 or 20 seconds, your hand would probably recover completely. Joe Kittinger proved this in 1960. He was a United States Air Force pilot, and he was part of a project called Excelsior. The idea was insane, even by the standards of the era. Kittinger rode a helium balloon to the edge of space over 100,000 feet and jumped, free fell toward the Earth from an altitude where the sky above you is black and you can see the curvature of the planet. During the ascent, the pressure seal on his right glove failed. His hand was exposed to near vacuum conditions, and he said nothing. He did not abort the mission. He made a decision, in that moment, that losing the use of one hand was an acceptable price for completing the jump. His hand swelled to twice its normal size. Twice. The tissue distended, the veins bulged. The fingers became useless sausages of swollen flesh. He could not grip anything with that hand for the entire 13-minute descent. The pain must have been extraordinary, but after he landed, and the pressure was restored by the thickening atmosphere at lower altitude, the swelling went down. Blood flowed normally again. Within 3 hours, his hand was completely back to normal. No permanent damage. Kittinger's hand survived because it was only his hand, a small area of skin connected to a body that was otherwise pressurized and oxygenated. The skin held, the blood vessels stretched but did not rupture. The exposure was limited and localized. It demonstrated something important. The body is tougher than you might expect. Human skin is essentially gas-tight. It does not burst in a vacuum. It swells, it stretches, it hurts, but it holds. The body can survive brief encounters with vacuum. But the key word is brief, and brief means seconds, not minutes. A small leak in a spacesuit, if caught immediately, might be survivable. You seal the area, you get back to the airlock, you repressurize. But a large breach, or a breach that goes undetected, is fatal. And the line between survivable and fatal is measured in the diameter of the hole, the rate of pressure loss, and the time to rescue, all of which depend on how much damage was done to those 13 layers. Those 13 layers. Think about it, 13 layers between a human being and the most hostile environment we have ever tried to work in. 13 layers between boiling alive from the inside and coming home to your family. I find that remarkable. Not in the cheap, hand-waving sense. I find it remarkable the way I find a suspension bridge remarkable, or a beating heart remarkable. It is an extraordinary thing that we can build a fabric sandwich that keeps a person alive in a place where nothing should be alive. And it is equally remarkable how fragile that protection is. How a scratch, a nick, a tiny puncture from a speck of orbiting debris can compromise the whole system. There is a version of the Soyuz 11 story that haunts me. In 1971, 3 Soviet cosmonauts were returning from the world's first space station, Salyut 1. Their names were Georgy Dobrovolsky, Viktor Patsayev, and Vladislav Volkov. They had spent 23 days in orbit, 23 days of scientific work, of looking down at the Earth from 200 miles up, of floating weightless through their tiny laboratory. Everything had gone well. They had broken records. They were heroes. They undocked from the station. They separated their descent module from the orbital module for re-entry. It is a standard maneuver. Explosive bolts fire, the modules pull apart, and the descent capsule with its heat shield begins its fall back to Earth. During that separation, a ventilation valve in the descent module jarred open. It was a valve designed to equalize pressure with the outside atmosphere during the final stages of descent, after the parachutes deployed and the capsule was dropping through breathable air. But it opened too early, 200 miles up in vacuum. They were not wearing pressure suits. At that time, the Soviet space program had decided that pressure suits were unnecessary inside the capsule during re-entry. They took up too much room. The Soyuz capsule is small. With 3 cosmonauts in their pressure suits, there was barely room to move. Someone made the decision that the extra space was worth the risk. It was a calculated trade-off. Comfort and mobility versus a layer of protection against an event that had never happened. The valve leaked. The cabin atmosphere vented into space over the course of about 30 seconds. Half a minute, one of the cosmonauts, Volkov, tried to close the valve manually. He had to unbuckle from his couch, reach the valve and turn it. He managed to get it halfway closed before the oxygen in his blood ran out, and he lost consciousness. 30 seconds. It was not enough time. And the capsule continued its automatic re-entry. The computers did not know the crew was dead. The parachutes deployed. The retro rockets fired. The capsule touched down on the steppes of Kazakhstan right on schedule. The recovery helicopters landed. The crew opened the hatch. They found 3 men who looked like they were asleep. No external injuries, no deformation of their bodies. No dramatic Hollywood gore. Autopsies later revealed hemorrhaging in the brain and lungs and gas bubbles in the bloodstream. Embolism. The textbook case. They were just dead. The air had left, and they had followed. After that, every Soyuz crew wore pressure suits during launch and re-entry. The capsule was redesigned to carry only 2 cosmonauts instead of 3 to make room for the suits. It stayed that way for more than a decade, until a larger capsule was developed. The lesson was learned. But it cost 3 lives to learn it. I think about margins when I hear stories like that. The margin between the valve opening and not opening. The margin between wearing a suit and not wearing one. The margin between a scratch and not a scratch. In physics, we like to talk about forces and fields and particles. We like equations, we like precision, and all of that is important, but sometimes the most important physics lesson is the simplest one. The difference between life and death can be astonishingly small. A 1/4-inch O-ring, 13 layers of fabric, a ventilation valve, a speck of dust moving at 36,000 miles per hour. Nature does not grade on a curve, it does not give partial credit. You either have enough pressure to keep your fluids liquid or you do not. You either have enough layers to stop the particle or you do not. There is no almost alive in a vacuum. And every time we send a human being into that vacuum, we are betting everything on the integrity of the engineering, on the quality of the materials, on the thoroughness of the inspections, on the accuracy of the risk calculations. We are betting that nature will behave the way our models predict, and that no unforeseen detail will slip through the layers. This is not an argument against spaceflight. I hope nobody walks away from this thinking I am saying we should not go to space. Quite the opposite. I am saying we should go, and we should go with our eyes open. We should go understanding what we are asking of the materials, of the engineers, and of the astronauts. Because the beauty of it, the real beauty, is not that space is safe. The beauty is that we go anyway. That we build 13 layers of protection against total annihilation, strap ourselves into a garment that weighs less than a suitcase full of books, and float out into a void that would kill us in the time it takes to tie a shoe. That is courage. Not the ignorant kind of courage. that does not know the danger. The informed kind, the kind where you understand exactly what the physics will do to you, and you open the airlock anyway. I have spent my whole career studying the fundamental rules of nature. I have looked at the behavior of subatomic particles, and the structure of the atom, and the strange counterintuitive logic of quantum mechanics, and I can tell you that the rules are the same everywhere. The same physics that makes water boil on your stove is the physics that makes your blood boil in a vacuum. The same thermodynamics that governs a pot of soup governs the surface temperature of a spacesuit in direct sunlight. There is no separate set of rules for space. There is just one set of rules, and in space those rules have sharper teeth because there is nothing between you and them. So the next time you scratch the back of your hand and barely notice, think about this. Think about the fact that you are living at the bottom of an ocean that is keeping you alive, and that if you were to rise above that ocean, the only thing standing between you and the physics of the void would be 13 layers of nylon, urethane, Kevlar, Mylar, and Gore-Tex, and that a scratch on the wrong layer in the wrong place at the wrong time is all it takes. That, my friends, is what it means to live in a universe that does not care whether you survive. The universe gives us the rules. Pressure keeps fluids liquid. Atmosphere blocks radiation. Insulation slows heat transfer. These rules are not suggestions, they are not guidelines. They are absolute. And the engineers who build spacesuits know this better than anyone because they work every day at the boundary between those rules and human ambition. I find that boundary the most interesting place in all of science. Not the comfortable middle where everything works as expected, but the edge, the margin, the place where one scratch is the difference between coming home and not coming home. If you were an astronaut, suited up, floating outside the station with the Earth rolling slowly beneath you, what would you be thinking about? Would you be looking at the view, or would you be looking at your gloves? I know what I would be doing. I would be checking my gloves.